mu I a squared over 2. Yep, that's what we had. Good stuff. And we can use a similar right-hand rule to determine the upward, the sort of monodirectionality of the current loop. We curl our fingers in the direction of the current, our thumb points in the direction of the magnetic field, the longitudinal, the on-axis magnetic field. Here's a picture of the magnetic field due to a section of a current loop. Note that the field lines off axis are not so well behaved. They are not circles. They're maybe ellipses. I hope that they're ellipses, but I'm not even sure that they are. They appear to be narrower on this side of the, inside the plane of the loop than they are outside the plane of the loop. And off the longitudinal axis, we need computational methods. Our integral, our analytical integration breaks down. Which is interesting because the on-axis one was so nice, so well behaved. An application for the calculation we just performed is the magnetic field created by the coils in an MRI machine. Typically, we need a strong magnetic field that is relatively uniform over a fairly large, a person-sized area, someone's head-sized area, basically. And the uniformity condition means that a single loop isn't so good. We really are interested maybe in a I don't know, I want a way to try to make a uniform field. Because at different points along the axis of a single loop, the answer changes. It's worth mentioning what if we are on axis in the plane of the loop? What if we're right at the center of the circle? At the center of the circle, x is 0, and we end up with just a squared to the 3/2, so a cubed, and we end up with the a squared in the numerator canceling an a squared in the denominator, leaving us with mu I over 2a. It's a nice, clean expression. Okay. Back when we were talking about electric fields, we had Coulomb's law. and we considered charge distributions, and we integrated Coulomb's law, essentially. We wrote the electric field of an infinitesimal charge, called it a point charge, and integrated over the entire thing. And then we started to, walking through the field, we started stepping in, I went to school in Boston. My wife and I lived in Boston for 6 years, and the I don't know if anyone is a fan or I'll call it an anti-fan of the Red Sox, but there by Fenway Park, there is an actual fen, a swamp or a marsh area. And there's some fields there, and it's between some colleges, so there's some green space. And it's a pretty popular hangout for geese. Now, but if you need to get from one side of that field to the other, you're stepping in goose poop. It's just a thing that's happening. And that's kind of what happened to us back when we were talking about electric fields and you doing the sort of vectorized integration. We got into a spot where we needed to care about the like domain of the trig substitution that we used. That's a pile of goose poop is what that is. It's, you can deal with it, but it isn't pleasant. So we looked for another way to relate the electric field created by a charge distribution to the distribution itself. And we ended up with Gauss's law. We talked about the net electric flux through a surface and how that was related to the charge enclosed in the volume bounded by that surface. We needed Gaussian surfaces, Gaussian cylinders, and Gaussian spheres to exploit the symmetry of the situations that we were examining. And we considered the flux, the electric flux through that surface. Now, we could define magnetic flux. In fact, we have already. We looked at the fact that Gauss's law, we could write it, we could ask for the net magnetic flux through a surface that bounds a volume. But it's going to be zero because magnetic field lines don't terminate. They're loops. If they enter the volume in question, they're going to leave, and the net flux is going to be zero every time. So Gauss's law for magnetic fields is not going to help us.